Hello and welcome back to the video series A Trip to the Moon. In these videos, we've used the game Kerbal Space Program and the websites GeoGebra and Desmos to illustrate principles of the calculus of parametric and polar equations. In this part of the series, the fifth and last part, we'll do some science while in orbit around the Mun and return, hopefully safely, back to Kerbin, completing our mission. So we left off in part 4 having reached a low altitude orbit around the Mun, and I thought it would be interesting first to use our speed and position while in orbit to estimate the mass of the Mun. From the tracking station on Kerbin, we can see the current altitude above the Mun at about 53 kilometers. We can see the speed at about 520 meters per second, and the semi-major axis of the orbit in the Kerbal Engineer display on the right side of the screen. That reads about 271,111 meters. To calculate the mass of the Mun, we can use the vis-viva equation. This equation relates the kinetic and potential energy of any object in orbit. We saw this equation in part 2 of this series. In this equation, m is the mass of the orbiting body, big M is the mass of the primary body that's being orbited, r is the distance between the orbiting body and the primary body, but we have to make sure to include the radius of whatever primary body we're orbiting. It's an easy thing to miss. You look at the altitude and use that as your distance, but actually you have to use the radial distance to the center of mass of the planet you're orbiting. So include the radius of the Mun here. A is the semi-major axis of the ellipse in the orbit, and capital G, that's the universal gravitational constant. It's the same value in real life as it is in Kerbal Space Program. The equation, this vis-viva equation, relates the kinetic energy 1/2 mv squared and the potential energy negative capital G, capital M, little m over r to a constant value, and thus it is an expression of the conservation of energy of an orbiting body. So this is the vis-viva equation, or let's say one form of it. It relates the kinetic energy here with the potential energy with some constant value that's determined by the gravitational constant, the mass of the primary body, the mass of the orbiting body, and the a value, the semi-major axis of the orbit. So the first thing you can do is cancel out the little m. It doesn't really matter what the mass of the orbiting body is. That's canceled out in my first step. This is how I wrote it back in part 2. So what I was doing back there was solving for an expression. I would, here multiplied both sides by 2, factored out the gravitational constant and the mass of the primary body. That's often used as what's called the gravitational parameter mu. And so solving for v, I got a formula for the velocity at any point based on the distance and semi-major axis. And of course the mass of the primary body and the gravitational constant. So we use this equation in this form to calculate speed at any point in an elliptical orbit. And that plus or minus there just can be interpreted to represent one direction or the opposite direction around that ellipse. So thus this formula relates the speed and current position and semi-major axis of the orbit with the mass of the primary body. But what I'd like to do here is rewrite this equation and solve for m. So I'm going to go back to this point right there where I had v squared by itself. V squared by itself in terms of the gravitational constant and the mass of the primary body and the radial distance and the semi-major axis. Let's go back to that point where we have the vis-viva equation in this form, and just let's isolate the capital M value. So we'll just divide by G and divide by this quantity in parentheses here. So isolating the mass of the primary body, we have v squared divided by the gravitational constant times the quantity 2 over r minus 1 over a, getting a common denominator and flipping the fraction. I get this formula for the mass based on knowing the semi-major axis, radial distance, and speed, and gravitational constant. So this is a formula now that can be used to compute the mass of the primary body given some orbital speed v, semi-major axis a, and distance r from the primary body. And actually got to be careful with that. It is not just simply the altitude, it's the radial distance to the center of mass of the primary body. So we have to include the radius of the Mun. By orbiting the Mun and perhaps using radar or by communication with the tracking station on Kerbin, we could imagine using this information to determine the value for the semi-major axis. I mean, we've got it recorded in the game, in the tracking station, and in the Kerbal Engineer display. So checking our speed and distance at any point in the orbit will give us values for r and v. And of course, g is the universal gravitational constant, a value that's the same everywhere in the universe. So let's give this calculation a try in the game. At this point in the orbit, we are at an altitude of about 70 kilometers, and our speed is approaching 492 meters per second. Using the fact that the Mun's radius is 200 kilometers, we have the following data. The semi-major axis of the orbit, that's A, it's about 271,111 meters. The distance from the center of the Mun to the orbiting spacecraft, that's the R value. That's the radius of the Mun, 200,000 meters, plus the 70,000 meter altitude. That gives me a radial position distance from the center of the Mun at 270,000 meters. The speed, roughly at that point when we hit 70,000 meters, that was about 492.2 meters per second. And the gravitational constant, that's g, that's 6.7 times 10 to the negative 11. So therefore we can calculate the mass of the Mun as follows with that formula that we had just derived, plugging in those values for A and the R, radial distance, this speed v, the gravitational constant, there's 2 times the A value, 271,111, minus 270,000 for the radial distance. So using a calculator and getting the value in the numerator, I get about 1.77 times 1.773 times 10 to the 16 divided by 1.816 times 10 to the minus 5. Division, I get about 9.76 times 10 to the 20 as my estimate for the mass of the Mun, based on our orbit, based on our radial position, semi-major axis, speed. This is the estimate for the mass of the Mun. Let's confirm that value with the data that's recorded in the tracking station. So yeah, there you go. Here in the tracking station, we are updating or confirming with the engineers on the ground that the mass of the Mun is 9.76 times 10 to the 20 kilograms. You can see that right there in the display. So pretty neat. Now that we have the mass, capital M, of the Mun, we can check this by using this value in the equation for orbital speed in a circular orbit. We saw this equation in part 1 of the series. The velocity is a square root of the gravitational constant, the mass of the primary body, and the orbital radius, or divided by the orbital radius. So if our value of m is correct that we just computed, we'll confirm the speed that we calculate here with the data that we observe in a circular orbit about the Mun. So in the video, I'll be attempting to circularize the orbit, but the required maneuvers, they're so small, it was a challenge to get into a perfectly circular orbit. So with a circular orbit at approximately 13 kilometers altitude, that is an orbital radius of approximately 213,000 meters, we can expect an orbital speed of approximately v equals square root, gravitational constant here. This is the mass that we just finished computing. This is the orbital radius approximation for the circular orbit that we'll in. We'll expect the speed to be around 553 meters per second. Let's see if that checks out in the game. pretty circular, somewhere between 13 and maybe 18 kilometer altitude, so 213,000 meters and 218,000 meters. But on the scale here, it still looks pretty close to a circle. You can see the eccentricity on the right is very near to zero. Okay, looks good. Pretty close to what we see in the game. Altitude between 13 and 14 kilometers and velocity approaching 553 meters per second. Okay, so we've made it to the Mun. We've successfully orbited and collected some scientific data about the Mun, its radius and mass. I think that's enough for this first mission. The ship we're using, the Kerbin X, was not designed for landing, so we'll have to wait for another trip to make that attempt. It'll be fun to try that sometime, but at this point, let's turn our attention to getting home. That's another important objective of this mission. In part 1 of the series, we calculated the escape velocity at a given altitude above Kerbin. Also, in another separate video I've made on velocity, circular orbits, and energy, I've discussed at length a really neat result that escape velocity is always the square root of 2 times the orbital speed at a particular altitude. So this result holds true anywhere in real life, anywhere in the real solar system, and anywhere in the Kerbin system. So let's use that result here to determine the velocity we need to escape the Mun's gravity to make our way home. At our current orbital radius of 214 kilometers, our speed is about 554 meters per second, and therefore the escape velocity should be square root of 2 times 554, which is about 783 meters per second. Thus, to escape the Mun's gravity, we need a delta V of about 230 meters per second. Now that's the increased velocity we would need to completely escape the gravity of the Mun. All we need to do here is escape the Mun's sphere of influence, and a delta V of about 200 meters per second will be sufficient to do that. So in the game, I'm adding a maneuver to increase the orbital speed by around the Mun by about 200 meters per second, which puts us on a trajectory to escape the Mun's gravity or sphere of influence and enter into an orbit about Kerbin. With the added velocity at around 750 meters per second, we'll be on a trajectory to escape the Mun's sphere of influence, and once that happens, our orbit will be determined by the gravity of Kerbin. And once the gravity field of Kerbin dominates our trajectory, we'll initiate some additional orbital maneuvers to enter into an elliptical transfer orbit that returns us to Kerbin. The goal at that stage is to create a trajectory with a periapsis inside Kerbin's atmosphere so that the atmosphere will slow us down. And at that point we can use our parachutes to further slow our descent and land somewhere, anywhere, hopefully safely, and preferably during the day. First, it's easier for the recovery crew to find us during the day, but also it makes for a more appealing looking video, at least one that's visible. There's a whole lot of fascinating math to explore here about this return orbit, like predicting where we'll land based on where the orbit enters the atmosphere. That kind of math gets really complicated really quickly though, and we've already achieved a lot in this 5-part series, so I'll save that for another video and another time. Instead, here I'm just going to eyeball the path home and hope it works out for a safe and visible landing. I am making some last-minute corrections there to the path just to try to get that landing during the day, make sure that the periapsis is in the atmosphere. That's it. Everybody looks okay. We made it. A successful trip to the moon. Okay, it was a trip to the moon. Thanks for watching, and I hope this has been an interesting and fun way to learn some of the calculus of parametric and polar equations.